Okay, so welcome. Even though this is a different lecture series, I thought that I should start because I worked with some agency. Actually, they are working for some secret purpose, but they gave me some of the portion to simulate. So I'll not go in that details. But I will try to give you some overall idea of the CFD simulation, which is extensively used in aerodynamics. So normally I use SolidWorks CFD module and COMSOL CFD module. It's a very good. Normally for any kind of coupled study I use COMSOL because it's a multi-physics, but normal CFD simulation, it's very quickly for the solution convergence point of view. This SolidWorks is good in my opinion, because whatever I used, I simulated, I got good result in SolidWorks CFD module. So I will just very briefly within few lectures I will try to cover the aerodynamics, aero modeling simulation using CFD. People who are students who are interested to make a small aeroplane, so they are not able to understand, they are not able to design the structure or to bring the stability to understand the aerodynamics. Hope this lecture series will be helpful. So today we are going to discuss, but one more thing I am telling, simulation is normally anybody can use the simulation tools. Today lot of simulation tools are available in the market, but the thing is, prior to use the simulation tool you need to understand the dynamics. Otherwise the boundary, because the accuracy of the result, if you give some boundary conditions, define some goals, some output will come, but how far it will be accurate, that depends on the how you are applying the boundary conditions to the model and how you understand the dynamics. If you understand the dynamics better way, then you can apply the boundary condition which is exactly equal to the practical cases, and in such case you will get some better result. Okay, so today we will understand every lecture we will first understand the dynamics and then we will simulate. Everything will be simulated. Every topic will be having two consecutive lectures. One is for understanding the dynamics and second is the simulation. Okay, so today we will calculate, today we will understand the lift, how to calculate the lift force of aircraft. Okay, so normally this is, I am not good, I'm not a good, I can draw it. It is just I tried to give you the concept. To say this is the aircraft and this is the wing, and the shape is like this, say airfoil. So normally in old, I have seen in old college, when this simulation tools, all these packages were not available, that time there was a in aero modeling, during the aero modeling, this kind of foil, it will be simulated in wind tunnel lab. This big wind tunnel lab, and their wind flow is created and the things are measured. The lift is measured practically. So lift means the upward force which is due to which the entire aircraft is floating. Okay, so that how it is happening. So first we will understand very roughly, so that during our modeling and simulation we can apply the boundary conditions in the better way. So this aircraft is moving with certain velocity with this direction. Okay, now the air, say the air molecule or the air particle, this is moving like this, like this, like this, like this. Okay, this is the air particle. Now we can assume this is a streamlined flow. Okay, this is a streamlined flow, and eventually from the structure of this wing, it is very easy to understand that this distance is lesser than this distance due to this curvature. Okay, so naturally the velocity at which the air particle moving in the bottom of the wing, say that is v1, and the velocity at which the air particle moving on the top of the wing, as this distance is more, the top distance is more, then definitely the velocity v2 should be higher than v1. Am I right? Time taken, so we can understand in this way. Time taken to move the air particle, as it is a streamlined flow, from this point to this point, it is same. So this distance is s1, and this top, this curvature, this is s2. Okay, so definitely this s2 is greater than s1. Now if I divide it by the time, so definitely this v2 should be greater than v1. Correct? Now we are coming to very basic principle, Bernoulli's law. So that is the static pressure plus the dynamic pressure rho v square by 2 plus the elevation pressure, that is always constant. So that is equal to P2 plus rho v square by 2 plus the elevation head, the pressure due to elevation head. So this elevation is more or less same, so this we can cancel it. Okay, now this P1 means the pressure P1 is the pressure at the bottom of the wing, and P2 is the pressure at the top of the wing. Okay, so this P1 minus P2 is equal to rho by 2 into V2 square minus V1 square. Okay, as this V1 is greater than V2, so this is a positive quantity, so definitely we can tell if this quantity is positive, then definitely this P1 is greater than P2. If such, then pressure at this area is higher than pressure at this area, so it will create one upward pressure. The resultant pressure is upward. Now if this length of the wing, and say the length of the wing is L and this width of the wing is B, then the cross sectional area is this one, and the total lift, okay, upward lift, that is equal to rho into L into B by 2 into V2 square minus V1 square. Okay, so this is a very rough understanding, but in the next lecture, so now this value should be when at steady state. So this should be equal to the total weight of the, so this F will work in this direction and the entire weight of the aircraft, it should work in this direction. If both are equal, then it will be floating. If the thrust is created, then it will move. Okay, so these are the very fundamental things, even though there are a lot of other things are involved. So this calculation, because by analytical method it is difficult, even though earlier it was done with like that only, using several approximations, but this problem, in the next lecture, this problem we are going to learn through simulation. So what should be the steps? We will create, first in a particular plane, we will create in this kind of one drawing, then this part will be extruded and create that wing shape. Then we will go to the CFD module. Okay, after going to the CFD module, we will define the computational domain. Okay, then we will define the velocity, and we will estimate for the goal we will estimate the pressure distribution on the top surface and the pressure distribution in the bottom surface. From there we will finally able to understand the total lift of the aircraft due to that particular shape of the wing. So this we are going to do in the next lecture using SolidWorks CFD module. So hope it is useful. Thank you so much.